Good morning and welcome to this session. This session was meant to program 8255A and to interface DAC 0800 and to explore one of its application like a function generator. This is the development board what we use in our laboratory. Now on my left hand side I have two 8255As which are programmable peripheral interfaces where the bottom 8255A is in the odd bank and the upper 8255A is in the even bank. Okay, we'll quickly try to learn how to program 8255A. I'll try to reproduce the conceptual diagram of 8255A to quickly understand how to program this 8255A. A255A, when we look inside, it has 4 registers, namely port A, port C, port B. Every port is a parallel port. Port A0 to port A7. These are the 8 pins. These are the 8 pins through which the byte what I write into the port A register will either go out or come in. Port C, for my convenience, I will logically break it into 2 parts, port C upper and port C lower. Specifically, port C upper drives the pins PC4, PC5, PC6, PC7. Port C lower drives the pins PC0, PC1, PC2 and PC3. Port B is an 8-bit port. PB0 to PB7 are the pins. So 8255A, which is a programmable peripheral interface, is an 40-pin DIP, and we have already understood 8 plus 8 plus 8, 24 pins. Now this 8255, when we plan it to be interfaced with Intel 8086, either of the lower bank or the higher bank will be driving 8 data lines through which we will be writing a command into the 4th register called command register. Command register. Port A is an 8-bit register, port C is an 8-bit register, port B is an 8-bit register, and the command register is also an 8-bit register. One of the 4 registers was selected by using 2 address lines, namely A1, A0. A1, A0, 00, we were diverted to port A register. 01, we were directed to port B register. 10, port C register. 11, command register. Okay. It's evident that I can either write a command or read the contents of any one of these registers when I plan a port as an output port. Okay. "8086 will be writing a command into this command register by selecting A0 and A1 to be 1, 1. Let's digest the command first. Since the command register is an 8-bit register, the command is also an 8-bit format. The 8th bit, the MSB, if it is 1, it's an indication to 8255 that I am trying to send a command describing the way how the port A registers are planned to work. Okay. Following MSB, MSB minus 1, MSB minus 2 were meant for describing the mode of group A. The members of group A are port A and port C upper. If the mode bits are made 0, 0, we are planning port A and port C upper in a simple IO mode. The rest of the modes are for handshaking. Since the members of group A are port A, the next bit was dedicated for describing it as an input port if I write 1 and an output port if I write 0. The next member of group A is port C upper. When I write 1 here, it is input. When I write 0 here, it is output. Next comes the mode definition bit for group B. The members of group B are port B and port C lower. The mode bit can be either 0 or 1. 0 indicates simple IO mode and the members of group B are port B and port C lower. When we want port B to be input, we write 1 and we want port B to be output, we write 0. The discussion is also true for the LSB. So, we have understood the command word sent for 8255A to describe the way how the ports work. let's quickly review DAC 0800. It's an 8-bit DAC which has 8 digital inputs which can be connected to any one of the port of 8255A the analog end of this DAC 0800 generates an analog equivalent current which is proportional to the digital word I keep in port A register, provided port A register is tailored to be an output port in simple IO mode. And we can drive this analog output current through an op amp IC 741 with an potentiometer RF to produce an Vout. Since the op amp ideal characteristics are known to us, because of high input impedance, no fraction of current enters into op amp, entire I out flows through RF, and I can approximate V out is equal to I out into RF. This is the module of DAC. You can watch 0800 accompanied by 741. This 741 op amp is having a feedback resistor RF. The way this RF was chosen was to generate an output analog value, analog voltage at this point X out, such that it drives 5 volts when I say FF. The full scale deflection voltage for this circuitry is 5 volts. Now, this Vout I can watch it on my CRO to produce the required function. Okay. I'll try to quickly make you understand how to program this setup to generate a square wave, leaving triangular wave and sawtooth wave as exercise. If I want to view a square wave on my CRO, analyzing one cycle of square wave, will have T on and T off, and this repeats. This should repeat. The idea for drafting assembly language program for this assignment was simple. I'll try to list out the sequence of steps. The first and foremost step is to program 8255A to mark port A as output. I have to mark port A as an output port. The next thing, port A is needed to drive the digital input of this DAC, and the analog output should be connected to CRO. Since the square wave contains logic 1 followed by logic 0 and this repeats, I can produce logic 1 by writing a digital value, say FF hexa, in port A register and call delay for T on. When the delay was done, I will write 00 hexa into port A register and I will call the same delay if I want to generate a symmetrical square wave. I mean, duty cycle is 50%. T on is equal to T off. Now we will attempt to write our first program to generate this square wave. I have gone through the datasheet of this development board and I have understood the control register address to whom I need to send command is available at FE07 hexa. I need port A address and I found it FE01 hexa. I will frame a command now according to the format discussed. MSB should be 1, MSB minus 1 and minus 2 describe the mode of group A. Simple IO mode 0 0. The members of group A are port A. I want it to be output. I don't worry about port C upper. Group B simple IO. Port B output, port C lower output, and this is the binary command I have framed to mark port A, port C upper, port B lower as output ports. All the ports are output ports. The command has to be sent to the control register address to make this happen. Now, exploring the dataset, using specialized I/O instructions. I can keep the address of control register in DX, copy the command in AL, and simply say out. So, at the address where A1 and A0 of my 8255 are double ones, the command to make all the ports as output ports was sent. I was able to make all ports as output ports. Okay. The port A address was written in DX, and the command to generate logic 1, say amplitude 5 volts, was chosen to be FFX, and it was sent to port A register. Now my CRO should specifically show me logic 1, 5 volts, and I want to continue this till the expiry of the delay. Once I enter into my main program from the delay routine, I wish to move from logic 1 to logic 0 for the same period. To produce logic 0, I have to switch my command from FF to 00 and send it to port A register and call the same delay. If this is symmetrical square wave, Once this was done, I will enter into an unending loop to keep producing the square wave. So I will end with short jump back can be placed here. So it was evident that I can see logic 1 followed by logic 0 followed by logic 1, logic 0 till I reset my machine. Function generator can produce square wave, triangular wave, sawtooth wave, of course, of specified amplitude and specified frequency. Let us muse how can we change the amplitude and frequency of the square wave we have generated. Logic 1 is FF, logic 0 is 00. We had a square wave of 5 volts amplitude. I want you to think what happens if I settle at some lower value less than FF? Yes, it's not going to be 5 volts. Now I have understood how to change the amplitude. Think about frequency. Frequency is the reciprocal of time period. Time period constitutes of T on and T off. The amount of time through which the square wave stays at logic 1 or logic 0 depends on delay. Now I will define the delay routine, which is a loop having no operation as the body of the loop. I will load a count into CX register, kill time 3 time periods for an 8086 which I am working with, decrement the count when it's not yet 0. I will go back to decay 2. I have counted in my hand, changing this count when I make it big. The time spent at logic 1 as well as logic 0 will go up. So time will go up and frequency will go down. And the converse is true. When the count goes down, time goes down, frequency goes up. Okay. I'm done with this part and I want you to try generating triangular wave and sawtooth wave. This is the classwork assignment which we'll try to crack. We will make up to write an assembly language program for the same setup to generate triangular wave and sawtooth wave. The triangular wave for one cycle looks like this. It starts at 0, 0. You see a gradual increment till the decided amplitude. You see a gradual decrement, and this repeats. Going to part B, sawtooth. Starts at 0, 0, keeps incrementing till FF and a sudden fall, and this repeats.